Okay, we're going to go through part 3 of this exam, Pearson Edexcel Physics AS level, Core Physics 1 from the linear specification. So I've done 2 parts already, did the multiple choice in the first section, and I did questions 9, 10, 11 and 12, I think, in part 2. We'll just have a look through as we go, as we skim through the pages. So if you haven't watched those first 2 videos, go back. They're in the same playlist on my YouTube channel. So don't forget to like, share and subscribe. We're trying to increase our subscribers to over 1,000. We're into the 900s already. Get a few each day. So we need your help. We need you to like each video you watch to show your appreciation. Share it with any friends who you think will benefit from watching them. That could be Edexcel Linear or Edexcel modular, and for that matter it helps anyone doing any syllabus because the content is the same in most syllabuses. Okay, so let's go and have a look. So multiple choice was the first 8 questions. So one of my students got 8 out of 8. Questions 9, moments, 10, a bit of projectiles, 11, Newton's laws, and 12, the first electricity question, which was on resistivity and practical skills like using micrometers and percentage uncertainties. So it looks like the linear throws in the Unit 3 questions, if you're doing International A-level, in the middle of the Core Physics 1, and probably will be the same in Core Physics 2. Okay? So these are good practice for people preparing for Unit 3 in the International A-level. So the next question is question 13, and it's showing a car on a slope at an angle of 11 degrees to the horizontal. The diagram shows a car being driven down a slope. So it's being driven down a slope. So I've kind of drawn the situation force diagram. The thrust of the engine is down, and it must be equaled by the drag or resistive forces in total. So it looks like we should start using the term resistive forces, okay, whenever we can. So let's just see if I can just put the pencil settings back on. For some reason I'm still having a problem with my pencil, so I'm using my finger. All right, so basically, so when you've got these resistive forces, the drag is part of it, but it could also be due to some friction, which is against the motion as well. So the thrust must be equal in length to the drag opposite, because Newton's first law applies. When there is constant speed, no acceleration, means the forces are balanced. Up and down, also the weight is balanced by the reaction at an angle of 11 degrees because of the slope. So remember, reaction is a normal contact force. So they want you to complete, from the situation diagram I've drawn above, they want you to complete a free body force diagram on the vehicle. So the vehicle is represented by the dot. The weight is downwards. You can't use the word gravity. Even in GCSE that was wrong. So some of my students are using that. Now the resistive forces are upwards, and you can see I've drawn the arrow longer than the driving force because part of the weight, because it's at an angle, is also helping the driving force. So part of the weight is also pulling the car down the slope. Okay, so the resistive forces has to not only balance the thrust, which I draw above, but it must also balance 11 degrees worth of the resolution of the weight down the slope. Okay, so that would be this angle here would be 90 minus 11. So it would be W cos 79. Okay, and then remember the reaction, which is on all the wheels, obviously, the normal reaction or the normal contact force will be at right angles to the plane of the slope. Make sense? So that's how you get 3 marks. 1 for resistive forces, 1 for the weight downwards, and 1 for the driving force, which is, oh no, that was given, so that's not correct. one for the normal reaction forces. Normal means at right angles to the slope. So I noticed that those who've done M1 already have an advantage over those who haven't, but hopefully you'll do it before your year 13 exam, and it won't put you at a disadvantage for the full course. So total resistive forces acting on the car, that's the backward force, is given as 2,530 newtons. Calculate the driving force required for the car to maintain a constant speed. So if it's maintaining a constant speed, we know that the forces must be balanced because acceleration will be 0. So the weight of the car is given to you. And remember that there is a slope of 11 degrees. So part of the weight is also helping the driving force. So the component of the weight down the slope is W sine 11, or as I explained before, it will be W cos 79. So you put the weight, it's already given to you in 2 newtons, so you don't need to do anything about working out the mass. Some people did that for some reason. You will find that the component of the weight down the slope is actually quite large. It's 2,290 newtons. So the force, the driving force, plus the W sine theta minus the resistive forces must balance each other. So they must add up to 0 because we have balanced forces. Okay? So the only unknown is F. So you can then just do the mathematics and you'll find that the difference between the two is 240 newtons. Okay? So the driving force, it doesn't require very much, because if you think about it, you could actually move down the slope just with the weight of the car. You could turn the engine off, yeah? And you can coast down the slope if the slope is steep enough and your car doesn't have too much friction preventing it from moving smoothly. Okay. Part B then reads, a very steep road may have a lane to one side filled with deep gravel. That's for safety. A vehicle with brake failure can then drive onto the lane with the gravel in it and will therefore be brought to rest as the vehicle's wheels sink into the gravel. So if they sink into the gravel, the wheels sink into the gravel, that means you'll have an increase in resistive forces in general due to the fact that they will resist the motion more. Okay, the graph shows the decrease in velocity of a van as it comes to rest in the gravel. So this graph is all about motion in the gravel. Okay, so just driving in the gravel seems to decrease the velocity at the maximum gradient, which is a tangent drawn to this point on the graph. And that allows you to work out the acceleration, which is what they're asking you to do. Now you can see the way I've done it on the graph. This is actually, the question is coming up. I've shown my tangent at the steepest point of the graph because we want to, they've asked us to work out the maximum rate of deceleration. So it'll be the steepest point of the graph. Okay, so you can see my values are clearly shown from 25 at the top for the change of velocity to 0 at the bottom. Use a large triangle, don't use a small triangle. The bigger your triangle, the smaller your percentage uncertainty in your calculations. And then the time difference is also shown on the finishing point of my triangle, 0.4 and 3.7. So this is the change in time. So I put both of these values into this equation here, and I like to show my calculation on the graph. Okay? So gradient figures shown at the steepest point of the line. So that's tangent, it's the instantaneous maximum acceleration. The question then says calculate the maximum decelerating force. Yes, that means the velocity is decreasing, it's going downwards, the slope, and the steepest point on the line, use a tangent, use a large triangle, you'll get 2 marks. If you've done what I've done, on the graph, show all that on the graph, it's easier. Then, once you've worked out the acceleration, because they've given you the mass of the van, You can then use Newton's second law to work out the mass times the deceleration force. The deceleration rate was 7.6 in my case, will give you 1.8 times 10 to the 4 newtons of decelerating force. So I put it as negative, yes, but they just want you to know the size of the force, so that I round it up to 1.8 times 10 to the 4. I didn't do a 3 significant figure one, so you can check my calculation for me if you wish. Okay, the force is negative because the gradient shows deceleration. Okay, so that's part 1. Part 2 then says describe the energy transfer taking place as a vehicle comes to rest in the gravel. Well, in the gravel, the energy transfer taking place is obviously linked to kinetic energy being lost. So the kinetic energy of the vehicle is transferred to some kinetic energy of the gravel. The gravel will no doubt move, therefore it gets some kinetic energy, and some transfer to thermal energy. And someone put sound. Well, sound eventually turns into thermal energy. Thermal energy could go to the tires, it could also go to the gravel, yeah, etc. So, and you can even put to the surroundings. So this is how you get the answer for the final part of this 11-mark question. Hope you found that useful. Okay, so a lot of physics is just being able to communicate clearly. Okay, clarity is key. Depth and detail is what gets you the rest of the marks. Question 14 is back to electricity. It says a light-emitting diode, an LED. And my students, we did it with a red diode, a blue diode, and a green diode if you weren't absent on that day. And we took readings of all 3 and compared them. And well done to those people who made the graphs on them. I know some of you have yet to do that. Okay, so it says a light-emitting diode is placed in a circuit with a fixed resistor. So here is the fixed resistor and the variable power supply. We also use the variable power supply, but when we did it, we actually did a more useful circuit diagram than that, but you didn't need to do it because the year 13 set up the circuit for you, and all you did was take the readings. Okay, we'll come back to that at a later time when we're in class. An ammeter and a high resistance voltmeter are also shown correctly wired up. The voltmeter is in parallel with the LED. The ammeter must also be in series. The graph shows how the current through the LED varies with potential difference across the LED. Okay, so when they took the values, you can see that initially the current doesn't increase until you reach a certain threshold voltage, which is just about 0.4 volts for the LED. And they want us to look at the value of the voltage in this graph. In the next question, they want us to look at the value of the voltage at 12.5 milliamps. So I've drawn my lines to show that at 12.5 milliamps, we have a LED voltage of 0.74 volts, and they're going to use this value. So if the LED has 0.74 volts, the rest of the battery's voltage will be across the fixed resistor. Okay, so you've got the voltage of the LED, and then you've got the voltage of the resistor, and together they will equal, according to Kirchhoff's laws, the voltage of the supply will equal the voltage across the components shared between them according to these values. Okay, so we now know that they're going to ask us about 12.5 milliamps when the potential difference across the variable power supply is 6.0 volts, 2 significant figures. The ammeter reading is 12.5 milliamps, so 3 significant figures. Use the graph to find I said the value of voltage for the LED, so I showed you on the graph. The value of the voltage of the LED is 0.74 volts. Show that on your graph, okay? It's part of showing your working, as part of your communication. Then we know that the rest of the 6 volts will be across the fixed resistor, so the fixed resistor gets 5.26 volts, okay? Once you know that, they want you to calculate the resistance of the fixed resistor. Well, we know that they're in series, so it will get to 12.5 milliamps. And you know the resistance is equal to the voltage across the resistor divided by the current through it, and you get 420.8 to 4 significant figures. I do that on purpose to show you when you put your final answer, you should really put it to 2 significant figures, okay? Because the data provided is 2 significant figures for the voltage, and therefore the 12.5 milliamps. You could put 3, but 3 would be 421 ohms, okay? So that's part A done. Part B then says the ammeter and voltmeter were removed from the circuit, and the variable power supply was replaced with a signal generator and an oscilloscope. So the signal generator, as you can see, is providing an alternating current, a sinusoidal variation of voltage, okay, or some kind of, when we see in the graph, is actually a square wave, okay. So the oscilloscope, remember, an oscilloscope measures voltage against time. Voltage, it can plot a graph of volts against time. So it's basically a voltmeter, which is varying, can measure AC voltage and plot it as a voltage against time graph, okay? So that's what they're doing now. So they're using, instead of a battery, they're using an alternating current or an alternating voltage, okay? So they've then shown the output of the signal generator is shown on the oscilloscope. So it's not a sinusoidal variation, it's what's called a square wave, okay? So it says the output varies between plus 6 volts and minus 6 volts. I've labeled that for you. So here is plus 6 volts at the top, and you can see the center is 0, the bottom must be at minus 6 volts. Points A, B, and C represents instants of time. So from A to B, the voltage is 6 volts. From B to C, the voltage is minus 6 volts. And then obviously from C to D, it goes back to plus 6 volts. So it alternates between plus and minus 6 volts abruptly. It's not a sinusoidal variation. So, explain why the LED flashes. The answer should refer to the output between the times A and C. So between A and B, the voltage is positive, 1 mark. Okay? The current will flow at that point, and we know when it was 6 volts, we were getting 12.5 milliamps. So that's the second point. The LED therefore lights up between A and B. Between B and C, we got negative voltage. And in the reverse direction, no current will flow through the LED, because the LED only allows current to flow when the voltage is in the positive direction. So the LED will not light up, another mark. Yeah? After C, this will happen again. So the LED only conducts when the voltage is positive, and the resistance of the LED, you could put, is very, very high in the reverse direction, which is why no current will flow. So that leads to it going on, off each time when it flips between the positive part of the square wave and the negative 6 volts of the square wave. Okay? So that's how you get the 6 marks, and you've got to change these notes into clear, lucid English. So the physics in English is more difficult than the maths in physics, or the English in physics, I should say. Okay, so there's question 14 done, another 10 marks. And question 15 is another electricity question, where it says electric cars are powered by a large battery within the car. The manufacturer of an electric car states that the battery stores a maximum charge of 110 amp hours. So with large batteries, we actually measure the amount of charge stores. Remember, charge is current times time, but instead of using amps and seconds, we use amps and hours. So 110 amp hours means the battery could give 1 amp for 110 hours before it runs out of charge. Or it could give 110 amps for 1 hour. Or it can give 55 amps for 2 hours. Okay, that's how much charge it contains. So amp hour is an alternative unit of charge for larger quantities. The graph shows how the current through the battery varies with time as the battery is charged. Okay, so as the battery is charged, it charges from the current increases as shown between 0 and 0.5 quite fast, and then it increases slowly between 17.5 amps to a maximum charging current of 20 amps. So you can see at this point it only reaches the maximum charging current for 4.5 hours. Okay, so what do they want us to do? So the graph is current against time in hours, and remember, charge is current times time. So the area underneath a current time graph is current times time. Therefore, the area underneath this graph is charge. Okay? So charge is all of this area up to the 5 hours, because they're going to ask us about 5 hours in the question. The manufacturer claims that it takes 5 hours to reach 90% of the maximum charge. Yeah? So the maximum charge being 110 amp hours. Yeah? So the maximum charge is this value here, 110 amp hours. So, criticize this statement. Since Q equals IT, I've written, the charge is the area under the current time graph, which I've done in green. Yeah, so I should have put this in green. So that's the area that we're talking about. Section of the graph from 0 to 5 hours is equivalent to between 0 and 0.5 hours. Yeah, it's a triangle, and if you work it out, the first triangle leads to a charge of this many amp hours. Check my maths. And then between 0.5 and 5 hours, there's a rectangular part. And then there's another triangle, which adds up to a total of 84.375 amp hours. So total charge in the first 5 hours, because it says it takes 5 hours to reach 90% of its maximum charge, which was 110 amp hours. Well, this only charges to the area under the graph equivalent to 88.75 amp hours. Okay, well, 90% of 110, yeah, is not the same as that, because you'll see that 88.75 out of 110, which was the total charge, we actually only get, fully charged to be 110, so we've only got after 5 hours 88.75. That's only 81% roughly. So it's only 81% charged, not 90% as claimed. Okay, so we've criticized it. It is not correct. Okay, so you can see where I've put the ticks, knowing that the area under the graph is charge, working out the total charge under the graph is 88.75 amp hours or thereabouts, and realizing that this is not 90% charged. There's different ways of showing that. Okay. Part B then says the manufacturer tested the car by driving at a constant speed along a horizontal track. Okay, so if it's driving constant speed along a horizontal track, remember, once again, we're talking about constant speed, so we're talking about balanced forces. And the manufacturer determined that the maximum range of the car was 160 kilometers when driven at that constant speed. Because obviously the maximum range will be when you don't accelerate too much, you go to constant speed, you have balanced forces, you don't have to overcome the extra work required to accelerate the vehicle. Show that the average value of the resistive forces must be about 800 newtons. Okay, so you've got to show that it's about 800 newtons. The efficiency of the car, they say, is 85%. And they say the energy stored in the battery when it's fully charged is 42 kilowatt hours. Now this time, instead of having amp hours, we've got kilowatt hours. Watts times hours is energy. Okay, but it's not in joules, so you've got to change it into joules. So 42 is 42,000. 42,000 times 3,600 becomes from kilowatts into joules. Because remember, there are 3,600 seconds in 1 hour. So the useful output, using the efficiency equation, change it so the useful output is the thing we want to work out. We know the efficiency, so efficiency multiplied by the energy input, which is 42,000 watts, times 3,600 seconds, will be a total of 1.29 times 10 to the 8 joules, to 3 significant figures. So if we know the useful output is equal to the work done against the resistive forces, so remember the resistive forces will be slowing down, and therefore it's working against this force. You can work against resistive forces like friction, so the force times the range will be the work done, because work done is force times distance, and we know the range is 160 kilometers. So if we want to work out the force, we change the subject to the equation. We know the useful output was 1.29 times 10 to the 8 divided by the range, and you get an answer of 803.25, accurate value or calculator value, and then you round it up to 1 or 2 significant figures. Either way, you have shown that the resistive forces doing the work against the energy of the car is using it up at 800 newtons approximately. Okay, the next part, it also is then going uphill. The manufacturer repeated the test on a sloping track. So it's a good way to test your vehicle, both on the straight road and a sloped track. This reduced the maximum range of the car. Why is that? Because it now has to also work not only against the resistive forces, against the motion, but against gravity. The potential energy gained is the loss of energy of the useful output of the car. So, at a new maximum range, the car had moved upwards through a height of 3 kilometers. So by the end of the range that is driven, it's worked against a rise in height of 3 kilometers. So the work done gain in potential energy against the potential energy. Work done against potential energy leads to reduction in the range. Yes, that's the concept. The change in the gravitational potential energy, therefore it comes from the output of the battery, is 1,300, which is the mass of the vehicle they're given, times the gravity, times the increase in height, and that's how much of the energy has gone into taking it up, a total elevation of 3 kilometers. That's quite high. Okay, assuming the car still operates at 85% efficiency, I'm saying, then the useful output that we worked from part 1, we can use it as being the force which we calculated in part 1, which is 800 and something newtons, 803.25, plus the new range this time. So imagine it's still working at the same resistive force, plus the work done we just worked out against gravity, which was 3.83 times 10 to the 7. The calculator value I had was 2 more significant figures shown here, and therefore the useful output from part 1 we calculated is here. So I've equated them underneath the terms below. The only unknown then is in Fs, and the only unknown in there is S. And we want to work out S. So if you can do the algebra using the accurate values, I got a value of approximately 113 kilometers when I did it and checked my values again. And therefore the loss of range before was, the loss of range is 160, which was before on the straight road, and now it's 113 kilometers, the new range. So the reduction in the maximum range going uphill will be 47 kilometers. So you can go 47 kilometers less in your range if you're working against gravity, which makes sense, doesn't it? Okay, so that brings us to the end for section A. Yeah, So you've noticed that up to here, all the questions have been mechanics and electricity. Now in the next section, section B, the questions could be on any part of the year 12 syllabus or specification. So the last part will be the 20 marks in this paper, and you can see, I'll just show you the first question. The first question is about the spring. So it's practical skills. Yeah, so question 16 is the spring was hung from a clamp, and then the spring was used to look at forces on there. Then you've got to draw a graph, then you do a gradient, then you've got to analyze the data. So this is about practical skills or the scientific method, yeah, being a physicist. And then the final question, so you normally have two, is about a washing line and the tension caused by putting a wet blanket on it. So there's a weight downwards, and then the washing line becomes tense, and you've got to do calculation of forces. So it's mainly mechanics. Well, one of the students was complaining, but I didn't revise Young's modulus, because it says with reference to Young's modulus, but obviously Young's modulus was covered when we did forces and mechanics, because it's a good time to do it. And you have to be able to cope with any question in the synoptic section, the final 20 marks in this paper for section B, and I'll go through this in a separate video. So I hope you found that useful. Once again, you need to make sure that you revise as much as possible for your exam next year, and the sooner you start working seriously as an A-level student, the sooner you'll reach the levels of students in the year above you, and you can speak to some of them, get advice from them, do communicate with them. They're very, very friendly, and they will be able to help you and give you advice on what to do and what not to do before it's too late. Don't wait until year 13. Okay, basically, if you're not at the grade C level at the end of year 12, we don't recommend you continuing with year 13, because the content gets more difficult, and then you have to remember the content from 2 years in the linear exam. So you really need to be working consistently from day one. If you're not, you're falling behind. Remember, you're competing with the top students from GCSE. You're no longer the top students. You're all good students for A-level, and it's the hard work, the hours you put in, that gives you the edge over the other students, and you're basically competing with all students globally. Okay? Right, well, thank you for watching this video. Don't forget to like, share, and subscribe. Pass it on to anyone you think might find this useful. Thank you for supporting my channel, and see you in the next video. Bye for now.